Welcome to Cosmic Sedation, your nighttime companion in the cosmos. Tonight, we're diving deep into the heart of mystery, what actually happens if you fall into a black hole. Subscribe and like for more cosmic adventures, and feel free to drop a comment with where you are listening from tonight and what time you usually drift off to sleep. As the stars begin to twinkle softly, let's embark on this tranquil journey together. Time stops at the edge of a black hole, not for you, but for everyone watching from afar. Imagine standing just outside the event horizon of a black hole with 4 times our sun's mass. The gravitational well around it is so deep that light itself cannot climb out once pulled in. This is the point of no return, 12 kilometers away from its center. Here, time dilates to such an extent that if you were being observed by friends far from the black hole, they would see you moving impossibly slowly. To them, your watch ticks at a fraction of its normal pace, while for you, moments pass as usual. The paradox deepens. The closer you get, the slower time moves, but the faster light must travel to escape until it can no longer do so. This is gravity's grip tightening on space-time. As you draw nearer, the black hole stretches space around you like a rubber sheet being pulled into an abyss. At 10 kilometers from its center, tidal forces begin to take hold. These forces stretch your body along one axis and compress it perpendicular to that direction, a process known as spaghettification. If you were standing upright, gravity would pull harder on the atoms at your feet than those at your head, causing a gradient of force across your frame. This tension can tear apart even solid materials at scales humans cannot perceive. The sensation is akin to an invisible hand stretching your body into a thin line. Inside this gravitational well, temperatures rise rapidly due to the sheer compression and friction. Near the event horizon, temperatures can reach up to 1 billion degrees Celsius. In contrast, the surface of our sun reaches only about 5,500 degrees Celsius. This extreme heat is not just thermal warmth. It's a byproduct of space-time itself being squeezed into an infinitesimal point known as the Singularity. The pressure and density are so immense that matter no longer behaves in ways we understand. If you could somehow withstand the forces, you would experience a realm where the very fabric of reality is being torn apart. Astronomers observe black holes indirectly by studying gas clouds falling into them. As this material spirals inward, it heats up and emits X-rays with specific energy levels. These emissions paint a picture of what's happening at the event horizon without directly showing us what lies beyond. The Event Horizon Telescope captured an image revealing the shadow of a supermassive black hole in 2019, darkness surrounded by a halo of light, bending around its invisible edge. This silhouette is not just the absence of light. It marks where space-time curves so deeply that even photons are trapped. Black holes offer a glimpse into the limits of our universe's laws. While they consume matter voraciously over unimaginably long timescales, 13.8 billion years for some, they can also evaporate via Hawking radiation. This process occurs when particles near the event horizon borrow energy from the vacuum and escape, causing the black hole to lose mass gradually. For a 5 solar mass black hole, This evaporation would take 10 raised to the power of 67 years, far beyond any human comprehension. In the meantime, they continue shaping the fabric of space-time around them, warping it into an endless abyss that defies our everyday understanding of reality. At the heart of a black hole lies an enigma known as the event horizon, a boundary so precise that it functions like a cosmic firewall, burning up any information crossing its edge and challenging our understanding of physics. The temperature at this boundary hovers around -230 degrees Celsius, colder than deep space. Yet, paradoxically, time dilates infinitely for external observers just outside the event horizon. Inside, however, nothing changes as you cross it. This firewall effect ensures that no information escapes once inside, creating what physicist Leonard Susskind calls an information puzzle. For a black hole with 5 solar masses, this boundary is about 4 kilometers in radius, smaller than some cities. At 10 kilometers from the event horizon, tidal forces stretch your body like taffy. Yet, for every meter you descend closer to the center, time slows by an infinitesimal fraction more than it did before. If you could observe Earth from this vantage point, its clock would be moving immeasurably faster than yours. This bizarre slowing of time is a consequence of extreme gravitational pull near the event horizon. At 4 kilometers in radius for our black hole, an area smaller than some cities, it contains more mass than the Sun. The immense pressure and friction at this point generate temperatures reaching 1 billion degrees Celsius, hot enough to melt protons themselves. Here, matter is compressed beyond comprehension, yet it remains invisible due to the escape velocity of light being exceeded. Strangely, if you were to fall into a black hole, your body would experience an eternity stretching before the final moments near the singularity. However, from the perspective of someone outside, witnessing this event, thousands of years might pass as they watch you approach the boundary. This discrepancy in perceived time is a stark reminder that our universe does not follow human intuition. The oldest known black holes are almost 13.8 billion years old, older than the most ancient galaxies. Yet they remain enigmatic, their event horizons shrouded in mystery. For humans, these cosmic phenomena are both awe-inspiring and confounding. The firewall at the edge of a black hole burns up information, leaving behind an inscrutable void, a place where our current understanding of physics begins to fray. Moreover, recent observations suggest that as matter spirals into a black hole, it emits X-rays with specific energy levels, providing astronomers with valuable insights into its properties. This phenomenon highlights the intricate dance between the extreme forces at play and our ongoing quest to understand these cosmic phenomena. The first image of a black hole's shadow was captured in April 2019 by the Event Horizon Telescope, revealing a dark circle against a bright background, a visual testament to the power of human curiosity and technology. Despite their immense age and size, these enigmatic objects challenge the very fabric of our understanding of information, space, and time. Each new discovery brings us closer to unraveling one of nature's most profound secrets. For instance, Hawking radiation suggests that over time, black holes might evaporate completely. But for a 5 solar mass black hole, This process would take approximately 10,000 billion years, a timescale far beyond human comprehension. In essence, the event horizon is not just a boundary, it's a gateway to an unfathomable realm where our current understanding of physics begins to fray. Imagine standing just a few kilometers from the event horizon of a black hole, where gravitational forces begin to stretch your body in different directions, a process known as spaghettification. Initially, you might feel only a slight discomfort as the pull starts to separate atoms at your extremities from those closer to your center. Each cell, each molecule, begins to experience this force differently. The difference in gravitational strength between your head and feet becomes significant enough that it stretches your body like taffy. As you draw closer, these differences grow exponentially. The pull on your toes is much greater than that on your head, causing you to elongate and thin like a noodle. This process accelerates rapidly as you near the point where light cannot escape. Here, time dilation makes this final journey seem longer from an external observer's perspective. Yet for you, it happens with alarming speed. Strangely enough, this effect mirrors the compression forces experienced by stars collapsing into neutron stars. Both phenomena are extreme expressions of gravity's relentless pull. Within 10 kilometers of the event horizon, the strain becomes unbearable. The force exerted on your toes is much greater than that on your head, causing you to elongate and thin like a noodle. This process accelerates rapidly as you near the point where light cannot escape. Here, time dilation makes this final journey seem longer from an external observer's perspective. Yet for you, it happens with alarming speed. The difference in gravitational strength between your head and feet becomes significant enough that it stretches your body like taffy. Consider for a moment that despite these violent forces, space itself remains perfectly smooth and continuous around you. The fabric of space-time is stretched just as your body would be in this environment, but unlike the matter within it, space-time continues unbroken. This paradoxical situation, where the very structure of reality remains intact while everything within it distorts, is a testament to Einstein's theory of general relativity. As you approach the event horizon, these forces are not just theoretical constructs. They become an immediate and terrifying reality. The temperature at the center of such a black hole can reach up to 1 billion degrees Celsius due to the extreme compression and friction generated by collapsing matter. This heat is not felt directly as your body elongates, but it does affect what remains of you in ways that defy imagination. The energy density here is so high that the physics governing normal matter break down, leading to phenomena like Hawking radiation at the quantum level, a process where particles are literally created from the intense gravitational field. As you reach the event horizon, time as we understand it ceases to have meaning for you. What would once be minutes or seconds in your experience stretch into eons for observers far away. Your body, by now a thin stream of matter, is pulled inexorably toward the singularity at the center of this cosmic maelstrom. This moment marks the end of what we can observe and understand about your fate, yet it also opens a window onto the deepest mysteries of physics, where space-time itself may be reshaped in ways that challenge our very perception of reality. Hawking radiation is a phenomenon that occurs at the very edge of a black hole, where space and time are so severely warped that even light cannot escape. This paradoxical zone operates under quantum effects that allow virtual particle pairs to momentarily appear and vanish near the event horizon. When these particles form, one may be trapped within while its partner escapes into the cosmos as Hawking radiation. For a black hole with 5 solar masses, this evaporation process unfolds over an unimaginable timescale of approximately 10 followed by 67 zeros years, a duration that far exceeds the 13.8 billion year age of our universe. In such vast temporal expanses, galaxies might form and disintegrate into cosmic dust through repeated cycles of star formation and supernovae explosions, highlighting how fleeting human lifespans are in comparison. The temperature of Hawking radiation corresponds inversely with the mass of the black hole. Smaller black holes radiate more intensely and evaporate faster than larger ones. A microscopic black hole with a radius smaller than an atom could emit enough energy to completely disappear within fractions of a second, whereas a black hole comparable in size to our Sun would persist for trillions upon trillions of years. As the black hole loses mass through Hawking radiation, its event horizon shrinks, accelerating the rate at which it emits energy. This creates a feedback loop. Less mass means faster evaporation and higher temperatures. Eventually, this leads to an explosive release of gamma rays when the remaining mass approaches the Planck scale, about 10 to the power of minus 35 meters in size. However, as the black hole evaporates, it also leaves behind a remnant particle known as a Planck relic, which could potentially interact with other particles and influence cosmic phenomena. Hawking radiation also introduces an intriguing paradox regarding entropy. According to classical thermodynamics, a system's entropy should increase over time. Yet, in the case of black hole evaporation, the total entropy decreases as the black hole shrinks and eventually disappears. This challenges our understanding of how information is preserved or lost in extreme gravitational environments, leaving researchers pondering whether there might be unknown mechanisms at play within these cosmic enigmas. For instance, some theories propose that information could be stored in complex quantum states beyond the event horizon. In addition to its implications for quantum mechanics and general relativity, Hawking radiation has practical applications in theoretical physics. It serves as a test bed for theories that attempt to reconcile the two fundamental forces of nature, gravity and quantum mechanics, at their most extreme limits. By studying this phenomenon, scientists hope to uncover deeper truths about the universe's structure and behavior at scales where conventional laws break down. Hawking radiation not only challenges our understanding of black holes, but also provides insights into the nature of time itself. Near the event horizon, time dilation becomes extreme, with time effectively stopping for an outside observer as matter approaches the point of no return. However, from the perspective of the infalling particles, time continues to progress normally. This dual perception of time creates a profound disconnect between what happens inside and outside the black hole's boundary. The radiation emitted by a black hole is not uniform. It carries with it information about the quantum state of the matter that fell into it. As the black hole evaporates, this information is gradually released in the form of Hawking radiation. This process raises questions about the conservation of information and the nature of entropy within gravitational systems. It suggests that while a black hole may appear to be an information sink from our perspective, it ultimately releases all data through its evaporation, a concept that challenges traditional views on how information is preserved or lost in extreme environments. This phenomenon also has implications for the fate of supermassive black holes at the centers of galaxies. Over time, these behemoths will gradually evaporate, releasing their energy into the cosmos as gamma rays and other forms of radiation. The final moments of a black hole's existence would be marked by an intense burst of energy, potentially observable across vast cosmic distances. This event, known as a black hole explosion, could provide valuable data for astronomers studying the early universe and the evolution of galaxies. In essence, Hawking radiation reveals that even in the most extreme conditions, nature finds ways to express fundamental principles like quantum mechanics and thermodynamics. It serves as a reminder that while black holes may seem like cosmic prisons, they are also gateways through which information can escape into the wider universe, challenging our understanding of both time and entropy on scales far beyond human experience. As you approach a black hole's singularity, time begins to stretch and distort in ways that defy our everyday experience. The closer you get to this point of infinite density, the slower time moves for you relative to distant observers. At 13.8 billion years old, some black holes have been around since nearly the dawn of the universe. Yet, from your perspective near the singularity, time stretches out infinitely as you hover just beyond the event horizon. The cosmic clocks ticking in faraway galaxies would seem to race forward at an unimaginable pace. The temperature near a supermassive black hole's core can reach up to 1 billion degrees Celsius due to extreme compression and friction. However, outside this region, space-time itself behaves as if it's under enormous pressure, causing light to bend around the black hole. This warping of space means that from your viewpoint, the stars in distant galaxies would appear increasingly squeezed into narrow arcs, creating an effect reminiscent of a circular panorama viewed through a fisheye lens. Within 10 to 20 kilometers of the event horizon, tidal forces begin to stretch you out like taffy, a process known as spaghettification. Yet these forces aren't uniform. They vary depending on your distance from the black hole's center. If you're closer to the singularity at one end of your body and farther away at the other, this uneven stretching can tear apart atoms in different parts of your body at varying rates. As you near the event horizon, the concept of time itself becomes a fluid rather than a rigid structure. For an outside observer, it would seem as though time for you has stopped entirely. But within this extreme environment, time dilation means that processes inside your body, the beating of your heart, the firing of neurons, continue to occur at ever slower rates. Each tick of your biological clock becomes more prolonged and drawn out. Once past the event horizon, Any information about what happens to you is lost from the observable universe. The point of no return acts as a cosmic censor, erasing all evidence of your journey into the black hole's interior. This boundary, defined by its escape velocity being equal to the speed of light, marks not just an end for you, but also the end of any communication with the outside world. Here, space-time is so profoundly curved that even light cannot trace its path back outwards towards distant stars and galaxies. The fabric of reality itself becomes increasingly unstable near a black hole's singularity. In this region, the very notion of now loses meaning as time no longer flows in a linear fashion. Instead, it spirals inward, converging on the singular point where all known laws of physics break down. This peculiar behavior of time near a black hole contrasts sharply with our everyday experience, where we can reliably measure seconds and minutes without significant variation. As you continue to fall towards the singularity, your perception of time becomes increasingly erratic. Moments that would normally pass quickly for an outside observer stretch out indefinitely. If you were able to communicate from this point, it would be as if each message took eons to reach its destination. This temporal dislocation underscores how profoundly different this environment is compared to the familiar world we inhabit. The extreme gravitational forces near the singularity not only affect time, but also dramatically alter your perception of space. Dimensions seem to blur and merge, creating a sensation where forward motion feels like falling through a dimensionless void. Your body would experience an intense pressure from being stretched in multiple directions simultaneously, a phenomenon that challenges our understanding of what it means to be solid or whole. At the event horizon's edge, light rays become trapped in an endless loop around the black hole's perimeter. This creates a ring-like structure known as the photon sphere, where light orbits the singularity at the speed of light itself. From this perspective, you would see repeated images of distant galaxies and stars distorted into swirling patterns, as if they were caught in the grip of some cosmic carousel. These visual effects highlight how space-time near black holes is far more complex than simple linear paths or straightforward geometries. As you approach the singularity, the fabric of space-time becomes so compressed that it no longer resembles anything familiar. The extreme density means that even light, which can escape from most other regions in the universe, cannot break free from this gravitational trap. This compression is so intense that it warps not just your perception, but also the very structure of reality itself, creating a realm where conventional physics breaks down and new, unexplored territories of existence emerge. At the edge of a black hole's event horizon, particles engage in an intricate dance that defies classical physics predictions. Here, quantum fluctuations create virtual particle pairs that spontaneously appear and vanish within fractions of a second, generating a zone of intense turbulence known as quantum foam. This phenomenon is so dynamic that it challenges our understanding of thermodynamics, with energy densities capable of powering thousands of Earths. The temperature near this boundary fluctuates wildly due to these rapid quantum events, reaching temperatures exceeding 1032 Kelvin in certain micro-instants. These changes create a paradoxical environment where particles can momentarily escape the black hole's gravity only to be reabsorbed instantly. This process is akin to turbulence in Earth's atmosphere, but on an inconceivably smaller scale. Each particle flickers and jitter, zigzagging due to interactions with quantum fluctuations. As you approach closer to the event horizon, these erratic movements become more pronounced. Particles no longer move in straight lines, but instead trace unpredictable paths through space-time. This chaotic motion mirrors turbulent weather patterns on Earth, yet operates at a scale smaller than an atom. The closer one gets, the more noticeable this effect becomes, creating a realm where predictability gives way to unpredictability. Intriguingly, these quantum effects have observable consequences. They manifest as faint ripples in spacetime detectable by advanced instruments like gravitational wave observatories. These tiny fluctuations provide insights into phenomena that challenge our conventional understanding of reality and offer clues about how gravity and quantum mechanics might be reconciled at these extremes. The interaction of particles near the event horizon hints at a deeper connection between the macrocosm and microcosm. Despite this chaos, there is an eerie tranquility to this region. Time itself slows down infinitely close to the boundary where gravity overtakes even light. This zone acts as a natural laboratory for physicists, offering glimpses into phenomena that challenge our conventional understanding of reality. The quantum activity creates a strange sense of order within the disorder, with particles behaving in ways that seem almost choreographed despite their randomness. As you venture closer to the event horizon, the sheer density of particles creates unique gravitational effects that warp spacetime further than predicted by classical models. Particles near this boundary experience extreme time dilation, where an hour for a distant observer could be years or even millennia for someone falling into the black hole. This phenomenon is akin to a ripple effect in water, but on an astronomical scale, where each particle interaction influences the surrounding fabric of spacetime. This region also demonstrates how quantum mechanics can dominate even at macroscopic scales near the event horizon. Particles constantly exchange energy through these interactions, creating a zone of intense radiation known as Hawking radiation. This process is so efficient that it theoretically allows black holes to evaporate over extremely long timescales, about 10 billion trillion years for a 5 solar mass black hole. Despite this slow rate, the concept challenges our understanding of stability and decay. The quantum interactions near a black hole's event horizon also reveal connections between seemingly unrelated physical phenomena. For instance, these processes mimic certain behaviors observed in superconductors and other systems where quantum effects dominate at large scales. This cross-pollination of ideas across disciplines provides fertile ground for new theories that bridge quantum mechanics with general relativity. These interactions near the black hole's boundary provide a glimpse into the fabric of reality itself, offering insights into how fundamental forces might intertwine in ways we have yet to fully understand. Each particle interaction is like a brushstroke on an infinite canvas, contributing to a larger picture that remains partially obscured by our current knowledge. The supermassive black hole at the center of our galaxy, Sagittarius A, contains a mass equivalent to 4 million suns compressed within an area roughly 10 times larger than our solar system's orbit around it. Yet, within this vast region, particles are subject to forces that can stretch them into thin filaments due to tidal effects, a process known as spaghettification. This phenomenon occurs when the difference in gravitational force between two ends of an object becomes significant enough to tear it apart. For a human falling towards such a black hole, these forces would begin to act approximately 20 kilometers from its event horizon. Despite the immense scale of a supermassive black hole, consider the microscopic particles that orbit close to it. These particles experience gravitational forces up to 10 billion times stronger than those on Earth's surface. At distances closer than 10 Schwarzschild radii from Sagittarius A, matter is compressed to densities exceeding 100 billion grams per cubic centimeter, conditions where atomic structures break down and quantum effects dominate over classical physics. This extreme compression is akin to packing a car into a sugar cube, illustrating the scale at which particles are influenced by such powerful forces. As these particles approach the event horizon of a supermassive black hole, they undergo significant transformations. The intense gravity warps spacetime so profoundly that time itself slows down relative to an external observer. For example, if you were watching someone fall into a black hole from afar, it would seem as though they froze just before crossing the boundary. This phenomenon is known as gravitational time dilation, and it underscores how drastically different physical laws operate within such extreme environments. The closer particles get to the event horizon, the more their behavior defies classical physics predictions. An unexpected fact: near the event horizon, quantum fluctuations might create temporary particle-antiparticle pairs that can annihilate each other, releasing bursts of radiation. Within these extreme conditions, particles near a supermassive black hole emit radiation across various wavelengths, including X-rays and gamma rays. These emissions are not random. They form distinct patterns that astronomers can observe and analyze. For instance, as matter spirals into the black hole, it heats up to millions of degrees Celsius, releasing vast amounts of energy in the process. This radiation provides valuable insights into the properties and behaviors of these cosmic behemoths. The extreme temperatures are a result of friction between particles colliding at incredible speeds, a reminder of how even microscopic processes can produce phenomena on astronomical scales. The age of some supermassive black holes rivals that of the universe itself, with many existing for nearly 13.8 billion years. These ancient entities have been witnesses to cosmic events far beyond human comprehension, from the formation of galaxies to the evolution of stars and planets. Their longevity is a testament to the stability of their environments despite the chaos occurring within them. Yet these black holes are not eternal. They eventually evaporate through Hawking radiation, albeit over incomprehensibly long timescales, around 10 sextillion years for one with 5 solar masses. This process suggests that even in the face of such massive forces, there is a subtle balance at play. For particles close to a supermassive black hole's event horizon, their journey ends abruptly as they cross the boundary and are lost forever from our observable universe. However, what happens beyond this point remains speculative. Theoretical models suggest that once past the event horizon, particles might be stretched into infinitely long strings before disappearing altogether or being incorporated into the black hole's mass. This process highlights the paradoxical nature of black holes. While they represent an end point for matter and energy, they also offer a unique window into some of the deepest questions about the universe's fundamental structure. In the early universe, just hundreds of millions of years after the Big Bang, stars began to form from clouds of hydrogen and helium. These ancient stars were massive, often containing dozens or even hundreds of times more mass than our Sun. Their short lifespans, measured in mere millions rather than billions of years, ended in catastrophic supernovae explosions that left behind black holes. These first-generation stars contained no elements heavier than hydrogen and helium. They had to forge the rest themselves within their cores under conditions so extreme that temperatures reached upwards of 10 million degrees Celsius. As these stars aged, they fused lighter elements into progressively heavier ones until iron was created. Iron fusion is energy-absorbing, not releasing it, which means once a star reaches this point, its core can no longer support itself against gravity. Remarkably, the black holes we observe today are not only remnants of these ancient stars, but also play a role in recycling cosmic material. As they pull in gas from their surroundings, some of this material may eventually be expelled back into space through powerful jets or winds. This recycled matter can then coalesce to form new stars and planets, continuing the cycle of cosmic evolution that began billions of years ago with those first massive stars. The paradoxical nature of these ancient black holes lies in their ability to both destroy and create. While they consume matter and energy, they also release radiation that can stimulate star formation elsewhere in their host galaxies. This balance between destruction and creation is a delicate one, played out over eons on scales incomprehensible to human perception. Yet this intricate dance of cosmic forces continues to unfold, with each event contributing to the ongoing evolution of galaxies. The conditions inside these ancient stars were so extreme that they could weld together protons and neutrons into new atomic nuclei, creating heavier elements that would eventually become part of planets and life itself. This process, known as stellar nucleosynthesis, is responsible for the iron in your blood, the calcium in your bones, and countless other elements essential to life on Earth. As these massive stars approached the end of their lives, they expanded into red supergiants before collapsing violently. The resulting supernovae explosions scattered enriched material across space, seeding future generations of stars and planets with heavy elements. This recycling process ensures that every atom in you has a cosmic origin, forged deep within the hearts of ancient stars that lived and died billions of years ago. The first image captured of a black hole's shadow in 2019 by the Event Horizon Telescope provided tangible evidence of these ancient cosmic monsters. This dark circle against a bright background is not just an abstract concept, but a physical reality, confirming theories that have been proposed for decades. The precision with which this image was taken underscores how far we've come in understanding these enigmatic objects and their role in shaping the universe. The evolution of black holes from ancient stars to the supermassive entities at the centers of galaxies is a process that spans billions of years. These supermassive black holes grow by merging with other black holes or accreting large amounts of material over time. This growth process can take place over billions of years, shaping the structure of entire galaxies as it progresses. Some black holes are so ancient that they formed less than 1 billion years after the Big Bang. Their existence challenges our understanding of how quickly such massive objects could form in the early universe. These early black holes may have played a crucial role in seeding the first generation of stars and galaxies, influencing the distribution of matter on cosmic scales. The temperature at the center of a supermassive black hole can reach up to 1 billion degrees Celsius, as measured by X-ray emissions from accretion disks. This extreme heat is generated through intense compression and friction as material spirals inward toward the event horizon, creating conditions hotter than any known environment in the universe. Astronomers have observed that gas falling into a black hole emits X-rays with specific energy levels, which are used to study its properties. These emissions provide valuable insights into the dynamics of matter near the event horizon and help us understand how black holes influence their surroundings. By analyzing these X-ray signatures, scientists can infer details about the mass, spin, and accretion rate of a black hole. Black holes can evaporate over time due to Hawking radiation, but for a 5 solar mass black hole, this process would take approximately 10 sextillion years. This means that while black holes are incredibly long-lived, they are not eternal. Over unimaginably vast timescales, even the most massive black holes will eventually fade away, leaving behind nothing more than a remnant of their once mighty presence in the cosmos. However, recent simulations suggest that before evaporating completely, some black holes might undergo explosive bursts, releasing significant amounts of energy and potentially observable gamma-ray signals. At the edge of a black hole's event horizon, light begins its peculiar dance, bending in ways that defy our understanding of what is visible and invisible. The curvature of space-time becomes so extreme here that even photons, which normally travel in straight lines, are forced into arcs. This warping acts like a lens, magnifying the light from distant stars and galaxies, making them appear as bright rings around the black hole's shadow. Astronomers call this effect gravitational lensing, a phenomenon where space itself bends reality. Imagine standing at the edge of a deep lake on a calm day. The water surface mirrors the sky perfectly until you throw in a stone, causing ripples to distort the reflection. Near a black hole, these ripples are space-time itself, and they can stretch out light from distant stars into arcs that circle the event horizon. This bending of light is not just a cosmic spectacle. It also provides us with a way to indirectly observe the unseen. Gravitational lensing around a black hole reveals more than just the shadow cast by its dark heart. It allows scientists to map the distribution of matter in distant galaxies and even test Einstein's theory of general relativity under extreme conditions. The precision required to capture these images is akin to reading a newspaper on Earth using a telescope placed on the moon. As you draw ever closer, time itself becomes an accomplice to this cosmic theater. Near the event horizon, clocks would slow down drastically from an outside observer's perspective, while for you, little change might be perceived until it's too late. The light bending around you isn't just a visual trick. It's a profound demonstration of how gravity can manipulate even the fastest particles in the universe. Light doesn't just bend here, it also becomes part of the black hole's identity. As photons are dragged into tighter and tighter orbits, they lose energy through gravitational redshift, eventually becoming invisible to external observers. This phenomenon explains why black holes appear dark despite their immense power. It's not that they don't emit light, but rather that they trap it within their confines. When an observer stands near the event horizon of a black hole, every second feels like just another tick of time. But for someone watching from afar, each passing moment stretches into what could feel like eternity. This is due to the intense gravitational pull warping spacetime so severely that time itself slows down infinitely close to the point of no return. Near a supermassive black hole with 5 solar masses, the temperature at its core can reach up to 1 billion degrees Celsius due to extreme compression and friction. Yet, paradoxically, the event horizon itself is incredibly cold, colder than deep space, at approximately minus 270 degrees Celsius. This contrast highlights how different regions of a black hole experience vastly disparate physical conditions. Gravitational lensing not only distorts light, but also stretches it in fascinating ways. Light from distant stars can be so bent that it appears to trace multiple paths around the black hole, creating what astronomers term Einstein rings. These optical illusions provide crucial data for scientists studying black holes' properties and their effects on surrounding space. The lensing effect serves as a window into regions beyond our reach, allowing us glimpses of distant galaxies otherwise obscured by intervening matter. This cosmic magnifying glass reveals details far too faint for direct observation alone, offering insights into the universe's structure at its most extreme points. Imagine standing at the edge of a galaxy where stars are born from clouds of gas and dust. In this cosmic nursery, black holes play an unexpected role in regulating the birth rate of new stars. These enigmatic objects, once thought to merely consume matter, actually contribute to the delicate balance that shapes galaxies over billions of years. The supermassive black hole at the center of our galaxy, Sagittarius A, weighs as much as 4 million suns, but occupies a space roughly 10 times larger than Earth's orbit around the Sun. Its influence extends far beyond its immediate vicinity. The temperature near a black hole can reach up to 1 billion degrees Celsius due to extreme compression and friction within the accretion disk, where matter spirals inward before disappearing into the event horizon. This intense heat ionizes nearby gas, causing it to glow brightly in X-rays. These emissions signal to surrounding clouds of gas that something extraordinary is happening, a process that can either trigger star formation or suppress it entirely. Paradoxically, while black holes consume material, their powerful jets and radiation often push away the very matter needed for new stars to form. This dual role highlights how black holes act as both creators and destroyers in galactic evolution. Black holes are not isolated entities, but rather integral components of their host galaxies. As gas spirals into a black hole, it forms an accretion disk, a swirling mass of material that can span millions of kilometers. The pressure and density within this disk reach astonishing levels, causing nuclear fusion to occur even before the matter crosses the event horizon. This process releases vast amounts of energy in the form of radiation, which then interacts with nearby clouds of gas and dust. In some instances, these interactions trigger star formation by compressing surrounding material into dense cores that can collapse under their own gravity, while in others, they prevent new stars from forming by dispersing or heating up potential stellar nurseries to temperatures above 10,000 Kelvin. Consider a black hole with 5 solar masses, an object that could fit within the orbit of Pluto if placed at the center of our solar system. Such a black hole has an escape velocity of 299,792 kilometers per second, exactly the speed of light. This boundary marks the point beyond which nothing can escape, including light itself. Interestingly, this region is not a static void, but a dynamic zone where matter and energy are constantly being drawn in and consumed. The material falling into the black hole does so with such force that it creates shock waves, compressing surrounding gas clouds. These shock waves can trigger star formation by forcing nearby material to collapse under its own gravity or disrupting cloud structures entirely. The age of the oldest known black holes is estimated to be around 13.8 billion years, close to the age of the universe itself. In this context, black holes have been pivotal in shaping galaxies since their inception. They not only regulate star formation, but also influence galactic structure through their gravitational pull and energy output. As gas falls into a black hole, it releases energy that can ionize or heat up surrounding material, affecting how stars form and evolve. This interplay between black holes and star formation has been ongoing for billions of years, contributing to the diverse array of galaxies we observe today. Black holes are not only cosmic giants, but also intricate participants in the delicate dance of galaxy evolution. They influence their surroundings by emitting powerful jets of energy that can span light years or more. These jets, composed of high-energy particles and radiation, interact with the interstellar medium, creating shock waves and compressing nearby gas clouds. This interaction can trigger star formation or prevent it, depending on the intensity and direction of the jet. In this way, black holes play a crucial role in shaping the destiny of galaxies, ensuring that they remain dynamic environments for billions of years. The instruments detecting gravitational waves from black hole mergers are capable of measuring changes as small as 1/100th of the width of a proton, far smaller than what can be perceived through human senses. While our eyes might miss such tiny movements, these precise measurements allow scientists to infer the properties of distant black holes with incredible accuracy. For instance, by analyzing the frequency and amplitude of gravitational waves, researchers can estimate the mass and spin of merging black holes. This information helps refine models of how these objects form and evolve over cosmic timescales. Black hole mergers are not isolated events. They occur within a complex web of interactions that shape galaxies. The energy released during such collisions can influence nearby star formation and even affect galaxy evolution. For example, the gravitational waves from merging black holes carry away angular momentum, potentially stabilizing or destabilizing surrounding gas clouds. This subtle interplay between cosmic giants and their environments underscores the intricate connections within the universe. The age of the oldest known black holes is estimated to be around 13.8 billion years, close to the age of the universe itself. These ancient cosmic behemoths were born in a time when galaxies were still forming, and stars were much more massive than those seen today. The temperature at the center of a supermassive black hole can reach up to 1 billion degrees Celsius due to extreme compression and friction. This heat is generated by matter falling toward the event horizon, accelerating and colliding with other particles in an intense dance of destruction. Each detected gravitational wave provides a unique glimpse into a different epoch of cosmic history. Some mergers occurred shortly after the Big Bang, while others are more recent events that have taken light years to reach us. By studying these signals, scientists can reconstruct the timeline of black hole formation and evolution, offering clues about how galaxies grow and mature over billions of years. For instance, the first image of a black hole's shadow was captured in April 2019 by the Event Horizon Telescope, revealing a dark circle against a bright background. But gravitational waves give us an alternative way to see these elusive objects. Black holes are not static entities. They evolve over time through various processes. For instance, some black holes accrete matter from their surroundings, growing larger with each meal of gas or dust. Others may merge with neighboring black holes, forming even more massive cosmic engines. These mergers generate powerful gravitational waves that travel across space, carrying the imprint of these events for eons. Understanding these dynamics helps us piece together the story of how galaxies and their central black holes have co-evolved over the lifetime of the universe. Astronomers observe that gas falling into a black hole emits X-rays with specific energy levels, which are used to study its properties. These emissions provide valuable insights into the environment near the event horizon, where extreme gravitational forces compress matter and heat it to millions of degrees Celsius. The intensity and pattern of these X-ray emissions can reveal details about the accretion disk's structure and the black hole's spin rate. This information is crucial for understanding how black holes grow and interact with their surroundings over time. In the depths of intergalactic space, two black holes, each with masses greater than 10 times that of our Sun, are on a collision course. Their orbits around one another tighten progressively, like dancers moving in synchrony toward an inevitable embrace. At this exact moment of their merger, space-time itself is torn and reshaped. The energy released from this event surpasses the output of all stars across the observable universe combined. This burst of power can be detected billions of light-years away through ripples in space, known as gravitational waves, cosmic thunder that feels more than it is heard. These waves ripple across the cosmos, distorting the very fabric of reality and leaving an imprint on space-time. Within microseconds, these two singularities merge into one larger black hole. The process is compressed into an instant, defying human intuition. As they coalesce, space-time warps and stretches, bending light paths and distorting time itself. This merger also triggers a cascade of high-energy particles and radiation spreading outwards at near-light speed. For a brief moment, the universe witnesses the most powerful event in its known history. The new black hole formed from this merger possesses a gravitational pull so strong it can stretch nearby objects into elongated shapes before consuming them entirely, a phenomenon known as tidal disruption. Yet, the event horizon remains stable, expanding only slightly to accommodate the increased mass without losing its integrity. This stability is crucial for maintaining the delicate balance of forces that define a black hole's nature. As astronomers on Earth detect these gravitational waves, they are witnessing an echo from the past. The signal travels at the speed of light, but carries information about events that occurred millions or even billions of years ago. Each wave encapsulates immense cosmic violence and transformation in a fraction of a second's worth of disturbance in space-time. This fleeting moment reveals not just a single event, but also hints at the grand cycles of star formation and death across galaxies. The merged black hole now occupies a region of space that is both familiar and alien. It continues to absorb matter from its surroundings, growing larger with each passing year. Yet, it subtly influences the structure of space-time in ways that could affect distant stars and galaxies for eons to come. This new black hole represents a fresh chapter in cosmic evolution, where the remnants of two ancient stellar titans are now intertwined into a single point of infinite density, poised to shape the future of its surroundings. The energy released during this merger would be enough to power all the stars in the universe for an eternity, a paradoxical thought given that black holes consume rather than emit light. The gravitational waves from such events travel across cosmic distances on the order of hundreds of millions to billions of light years, eventually reaching sensitive detectors on Earth like LIGO and Virgo. These instruments measure changes smaller than a proton's width, far beyond what human senses can perceive. Each detection provides valuable data about the nature of these enigmatic objects, contributing to our understanding of how black holes form, evolve, and interact with their environment. This cosmic dance continues long after the initial merger has occurred. The newly formed black hole settles into its new state, radiating gravitational waves as it adjusts to its altered mass. These waves carry not just a snapshot in time, but also a message from epochs past, reminders of the universe's grand cycles and the intricate balance between destruction and creation. Each ripple through spacetime is a signal from the stars, encoded with information about how these cosmic titans came to be and what role they play in shaping the cosmos. In the aftermath of this merger, the black hole's event horizon expands to accommodate its new mass. This expansion occurs over an incredibly short period, lasting mere fractions of a second. The surface area of the event horizon increases by about 10 kilometers squared for every solar mass added. This rapid change in size is akin to inflating a balloon at an astronomical scale. However, this expansion also leads to a surprising phenomenon. The temperature near the newly formed black hole's event horizon drops dramatically as it absorbs more matter, cooling down faster than expected due to its increased surface area. The temperature near the newly formed black hole's event horizon reaches extremes that challenge our understanding of physics. At its center, temperatures can exceed 1 billion degrees Celsius due to extreme compression and friction. This heat is generated as matter falls into the black hole, colliding with other particles in a process known as accretion. The energy released during this process far exceeds the luminosity of any star. The gravitational waves produced by such an event are not only powerful, but also incredibly precise. They carry information about the masses and spins of the merging black holes, allowing scientists to infer details about their origins and evolution. These waves travel at the speed of light, carrying with them a record of cosmic events that occurred long before humanity existed. The merged black hole will continue to grow as it consumes nearby matter. Over billions of years, it may merge with other black holes or accrete gas from its surroundings, further increasing its mass and size. This process contributes to the formation of supermassive black holes at the centers of galaxies, playing a crucial role in galactic evolution. The energy released during this merger is equivalent to converting 3 solar masses into pure radiation, enough to power all stars in the observable universe for an entire year. This paradoxical event underscores the immense power contained within these cosmic phenomena and challenges our understanding of how such vast amounts of energy can be unleashed in a single moment. As matter spirals toward a black hole, it forms an accretion disk, a dense ring of gas and dust where temperatures can reach millions of degrees Celsius due to friction between particles. This searing hot region is the last visible stop for any material destined to cross the event horizon. The sheer intensity of these collisions generates X-rays that astronomers observe from Earth, offering us a glimpse into this cosmic maelstrom. Within a few kilometers of the black hole's edge, gravitational forces become so extreme they stretch and tear apart everything that ventures too close. This process, known as tidal disruption, occurs in a region smaller than many cities on Earth, yet capable of exerting incomprehensibly powerful forces. Any object would be stretched into a long, thin filament, a fate named spaghettification. Within this narrow band, the force difference between your head and feet could become so extreme that it would separate atoms at your extremities from those closer to your center. At the edge of the accretion disk, matter moves in intricate patterns, swirling around the black hole's event horizon like water circling a drain. The closer to the event horizon, the faster this material travels, eventually reaching speeds near the speed of light. This spiraling motion follows specific paths determined by gravity and angular momentum. For an observer far away, time within this zone appears to slow down dramatically due to gravitational time dilation, an effect so pronounced that it would seem as if matter lingers in a state of hesitation before disappearing into the black hole. The accretion disk serves not only as a barrier, but also as a conveyor belt for matter destined to cross into the black hole's event horizon. The temperature here can reach up to 10 million degrees Celsius, causing ionized gas to emit powerful X-rays. These emissions follow predictable patterns that reveal the properties of the black hole itself, including its mass and spin rate. From Earth, these signals provide critical information about the inner workings of black holes, allowing scientists to study phenomena otherwise invisible. Imagine standing at the edge of such an accretion disk. You might feel weightless, yet experience extreme acceleration, akin to being on a roller coaster that never stops climbing. The light around you would be severely warped, bending and stretching until it forms rings and arcs around the black hole's shadow. This phenomenon is not just a visual spectacle, but a physical process where photons struggle against the intense gravitational pull of the black hole. For every photon that manages to escape, countless others are drawn in, creating an eerie halo of light. As matter finally crosses into the event horizon, it becomes part of a region where time as we know it ceases to exist. The extreme curvature of space-time at this boundary warps even light itself, creating a shadow around the black hole. This shadow is not an image of emptiness, but rather a testament to the overwhelming force that governs everything within its reach. Once inside the event horizon, any object or particle is irrevocably drawn toward the singularity at the center, where all known physical laws break down. Imagine you are floating in space near a black hole, an object so dense that not even light can escape its grasp. At its core, this celestial body may hold a secret far beyond mere gravitational pull, the potential for wormholes. These theoretical shortcuts through space-time could connect distant parts of the universe, though none have been observed yet. A 5 solar mass black hole would create an event horizon with an escape velocity equal to the speed of light, approximately 299,792 kilometers per second. Wormholes, if they exist, are not just theoretical constructs. They challenge our understanding of space and time. They could potentially allow travel across cosmic distances measured in billions of light years within fractions of a second from a human perspective. This concept introduces an intriguing paradox. While black holes pull everything toward them, wormholes might represent a way out or through space-time itself, offering shortcuts that defy the usual paths light must follow. The idea of traversing such a structure is both thrilling and unsettling, presenting a possibility where time and space are bent beyond recognition. Let's focus on the specific properties of these theoretical bridges. A wormhole would require exotic matter with negative energy density to stabilize it against collapsing. This substance differs fundamentally from what we experience in everyday life. It defies conventional physics by exerting pressure outward rather than inward. The notion of using such material to create a stable passage raises questions about the nature of reality and how our universe operates at scales beyond human comprehension. If confirmed, wormholes could offer not just a means of travel, but also insights into the very fabric of existence. In the heart of a black hole, space-time is so severely warped that it behaves almost like a rubber sheet stretched to its breaking point. Near this extreme environment, quantum fluctuations might play an unexpected role in the formation or stabilization of wormholes. These minute variations in energy can lead to phenomena we are only beginning to understand, such as the potential creation of temporary tunnels through space-time. The scale at which these effects occur is so minuscule that they challenge our ability to observe them directly, yet their implications stretch across billions of light years. Consider for a moment what it means if black holes and wormholes are interconnected in this way. Black holes with masses similar to several suns could serve as gateways linking different regions of the universe, each holding secrets about its formation and evolution. The oldest known black holes are estimated to be 13.8 billion years old, nearly as ancient as the universe itself. This suggests that these cosmic phenomena have played a role in shaping our understanding of time, space, and even life on Earth from their very beginnings. One unexpected fact is that if you were to fall into such a wormhole, instead of being pulled toward an inevitable singularity, you might find yourself spit out at the other end, potentially millions or billions of light years away in an entirely different part of the universe. The existence of wormholes remains speculative at this stage, but their theoretical implications are profound. They offer a glimpse into a universe where shortcuts exist between distant galaxies or perhaps even different points in time. The idea challenges conventional wisdom about the nature of travel and communication across cosmic scales. While we have yet to observe these structures directly, ongoing research continues to explore the possibilities they present for our understanding of physics and the cosmos as a whole. In the vicinity of a black hole, clouds of gas and dust swirl in complex patterns, drawn toward the event horizon by overwhelming gravitational forces. These accretion disks can extend for millions of kilometers, but are compressed to densities far exceeding those on Earth. Within these disks, temperatures can reach 13.8 billion degrees Celsius, a heat so extreme it defies comprehension. The intense pressure forces hydrogen atoms to fuse at rates billions of times faster than within a typical star, releasing vast amounts of energy and creating some of the most luminous objects in the universe. As stars orbit supermassive black holes, they trace elliptical paths that take them perilously close to the event horizon. Near this boundary, tidal forces stretch these stars into elongated shapes, sometimes even disrupting their surfaces or stripping away their outer layers. This phenomenon illuminates how space warps and distorts time itself in these regions. For instance, While light from distant galaxies might take billions of years to reach us, the light emitted just outside a black hole's event horizon is stretched into an infinite loop by the immense gravitational pull. Accretion disks emit powerful jets of high-energy particles along the black hole's axis, stretching for thousands of light years. These relativistic jets form when magnetic fields channel some of the infalling material, accelerating particles to near-light speeds. This process creates beams of energy and matter that interact with surrounding interstellar medium, potentially influencing star formation in distant regions of galaxies. The radiation from these jets can vary across the electromagnetic spectrum, offering astronomers unique insights into the physical conditions near the event horizon. The elements within accretion disks were forged in ancient stars that died before our sun even existed. As they spiral inward, these materials carry a cosmic history with them. The intense pressure and heat within the disk cause these elements to mix and interact in ways that are not seen elsewhere in the universe. This process not only fuels the black hole, but also contributes to the formation of new stars and planets far from the event horizon. The energy released by accretion disks can significantly impact interstellar gas and dust, affecting star birth rates within nearby clouds. By heating these materials to temperatures up to 10 million degrees Celsius, the disk disperses necessary elements, making it less likely for stars to form in these regions. For example, radiation pressure from the disk can push away dense molecular clouds that would otherwise collapse into new stars, reducing local star formation rates by up to 30% over millions of years. This intricate relationship between black holes and their galactic environments underscores how these cosmic phenomena play a crucial role in shaping the universe we observe today. As matter spirals toward a black hole, it forms an accretion disk where temperatures can reach millions of degrees Celsius due to friction between particles. This searing hot region emits radiation across various wavelengths, including visible light, X-rays, and radio waves. Each type of emission provides clues about the mass and spin rate of the black hole, as well as details about its chemical composition. The energy emitted from these disks not only illuminates the extreme conditions near a black hole, but also carries information that can be detected across billions of years and trillions of kilometers, offering glimpses into the very earliest epochs of the universe's history. The process of Hawking radiation begins with quantum fluctuations near a black hole's event horizon, where pairs of virtual particles spontaneously appear and vanish. One particle falls into the black hole while its counterpart escapes, contributing to an outward glow that gradually saps the black hole's energy. For a black hole with 5 solar masses, this evaporation would take approximately 10 sextillion times the age of our universe, a timeframe so vast it challenges human comprehension. This radiation is not felt as heat in the traditional sense, given there are no molecules to carry thermal energy in the vacuum of space. Instead, the emitted particles grow more intense, reflecting the extreme conditions near the event horizon. As the black hole shrinks, its temperature increases exponentially, reaching billions of degrees Celsius at its core due to extreme compression and friction. This radiation is composed of discrete packets of energy, each carrying a minuscule fraction of the black hole's mass. In essence, every photon represents a tiny piece of history, tracing back to the formation and eventual dissolution of an immense cosmic entity. The particles emitted are not uniform, but vary in their specific energies, providing astronomers with valuable information about the black hole's properties. Interestingly, as the black hole approaches its final moments, it emits more high-energy gamma rays than lower-energy photons, a phenomenon that could offer insights into the quantum nature of gravity. When a black hole evaporates completely, it leaves behind no physical remnants, only its faint afterglow in the form of Hawking radiation. This final burst of energy would be detectable by advanced instruments if observed today, offering a glimpse into the ultimate fate of these enigmatic objects. The complete disappearance of a black hole represents not just an end, but also a transition, as its mass and energy are redistributed throughout the universe. For instance, the remnants could contribute to cosmic microwave background radiation or form new stars and planets through processes like nucleosynthesis, where heavy elements are synthesized from lighter ones. The evaporation of a black hole is a slow and deliberate unfolding of events across unimaginable timescales, with time itself playing an intricate role in this cosmic drama. The extreme dilation of time near an event horizon stretches out the process of evaporation, making it a gradual phenomenon rather than an instantaneous one. This slow dissolution highlights how even the most powerful forces are constrained by the passage of time, ultimately leading to the breakdown of these formidable structures into mere particles of energy in the vastness of space. In the deep future, when black holes have completely evaporated, they will leave behind a universe that is fundamentally different from what we observe today. The remnants of their mass and energy will be scattered across galaxies, contributing to the cosmic microwave background radiation, or perhaps forming new stars and planets through nucleosynthesis processes. This process underscores the interconnectedness of all matter in the universe, where even the most extreme phenomena eventually contribute to the fabric of space itself. It is a reminder that every particle has its own story, intertwined with the history of the cosmos. The paradoxical nature of Hawking radiation lies in the fact that it allows black holes to lose mass over time, despite their reputation for swallowing everything they encounter. This phenomenon challenges our understanding of gravity and quantum mechanics, revealing unexpected connections between seemingly unrelated forces. For instance, the iron in your blood was once part of a star that died before our sun existed, illustrating how cosmic processes are deeply intertwined with human existence. As we consider the fate of black holes, it becomes clear that their eventual evaporation is not just a distant event, but a process that has been unfolding since the birth of the universe itself. The process of Hawking radiation begins with quantum fluctuations near a black hole's event horizon, where pairs of virtual particles spontaneously appear and vanish. One particle falls into the black hole while its counterpart escapes, contributing to an outward glow that gradually saps the black hole's energy. For a black hole with 5 solar masses, this evaporation would take approximately 10 sextillion times the age of our universe, a timeframe so vast it challenges human comprehension. This radiation is not felt as heat in the traditional sense, given there are no molecules to carry thermal energy in the vacuum of space. Instead, the emitted particles grow more intense, reflecting the extreme conditions near the event horizon. As the black hole shrinks, its temperature increases exponentially, reaching billions of degrees Celsius at its core due to extreme compression and friction. This radiation is composed of discrete packets of energy, each carrying a minuscule fraction of the black hole's mass. In essence, every photon represents a tiny piece of history, tracing back to the formation and eventual dissolution of an immense cosmic entity. The particles emitted are not uniform, but vary in their specific energies, providing astronomers with valuable information about the black hole's properties. When a black hole evaporates completely, it leaves behind no physical remnants, only its faint afterglow in the form of Hawking radiation. This final burst of energy would be detectable by advanced instruments if observed today, offering a glimpse into the ultimate fate of these enigmatic objects. The complete disappearance of a black hole represents not just an end, but also a transition, as its mass and energy are redistributed throughout the universe. This process highlights how even the densest structures in the cosmos eventually return to simpler forms, underlining the cyclical nature of cosmic phenomena. The evaporation of a black hole is a slow and deliberate unfolding of events across unimaginable timescales, with time itself playing an intricate role in this cosmic drama. The extreme dilation of time near an event horizon stretches out the process of evaporation, making it a gradual phenomenon rather than an instantaneous one. This slow dissolution highlights how even the most. The boundary around a black hole, known as the event horizon, presents an optical illusion for distant observers. Light from objects approaching it becomes increasingly redshifted until it disappears entirely. This phenomenon is due to gravitational lensing, where the immense gravity of the black hole bends light rays in such a way that they cannot escape. For instance, a clock falling into a black hole would appear to tick slower and slower to an external observer, not because time stops for the clock, but because the light required to carry its information takes longer to escape. Astronomers have observed gas clouds spiraling toward black holes in a process known as accretion. As these clouds approach the event horizon, they heat up due to friction and compression. This heating causes them to emit X-rays at specific energy levels that scientists can analyze to infer properties of the black hole. The temperature near the event horizon reaches millions of degrees Celsius, far hotter than any stellar core, illustrating the extreme conditions within this region. For an observer close to a black hole's event horizon, tidal forces begin stretching their body in different directions, a process known as spaghettification. These forces are so intense that they can rip apart atoms and molecules, creating long, thin shapes. This effect occurs because gravity varies significantly over such small distances near the boundary. The paradox lies in how close observers experience rapid changes, while distant observers see time slow down for those approaching the event horizon. Additionally, an observer falling into a black hole would notice that their own watch appears to speed up as they approach the event horizon, making it seem like time is passing normally from their perspective. The age of some black holes approaches 13.8 billion years, making them older than most galaxies. These ancient cosmic entities have been witnesses to epochs of star formation, galaxy mergers, and the evolution of cosmic structures. Their long history provides unique insights into the early universe's initial conditions and how it has transformed over time. The oldest known black holes are relics from when the universe was just a fraction of its current age. Notably, these ancient black holes have been found to possess spin rates that suggest they formed through highly energetic processes, such as multiple mergers of smaller black holes, which challenges our understanding of their formation mechanisms. The event horizon also plays host to an intriguing phenomenon: gravitational lensing. This effect causes light rays from objects behind or near the boundary to bend around the black hole, creating multiple images of the same object. For example, in 2019, astronomers observed a quasar that appeared as 4 distinct images due to this bending of light. Each image represents a different path taken by the light before reaching our telescopes, providing valuable data for studying the mass distribution and dynamics of the black hole. At the event horizon, time dilation reaches its extreme. An observer far from the black hole would see someone falling into it take an infinite amount of time to cross this boundary. However, for the person falling in, crossing the event horizon happens almost instantaneously. This paradox highlights the complexity of spacetime near a black hole and challenges our understanding of time as a linear concept. The immense gravitational forces warp time so profoundly that what seems like an eternity from afar is merely a fleeting moment for those who venture too close. Since the universe began, stars have been collapsing into black holes upon their death. This ongoing process has shaped galaxies and influenced the cosmic landscape for over 13.8 billion years. Each time a massive star exhausts its nuclear fuel, it implodes under gravity's relentless pull. The core collapses with such force that even light cannot escape once past a critical boundary, the event horizon, defined by Einstein's theory of general relativity. This collapse occurs across the cosmos without cease, an ancient and unyielding cycle of birth and death for stars. In contrast to our Sun, which will expand into a red giant before cooling peacefully, these massive stars end their lives spectacularly in supernovae that seed the galaxy with elements essential for life. The process begins when the star's core can no longer sustain fusion reactions, leading to an inward collapse followed by an outward explosion. Imagine standing near such a collapsing star just moments before it forms a black hole. The gravity here is so intense that it warps spacetime around you, distorting light and time itself. At the core of this newborn black hole, temperatures reach up to 1 billion degrees Celsius due to extreme compression and friction between particles. Yet, paradoxically, at its event horizon, the temperature hovers just above absolute zero. This coldness is not because there's a lack of heat, but rather because no matter can escape to radiate energy outward once it crosses this point. The pressure within such an environment exceeds any human comprehension, reaching levels that would crush even the strongest materials into oblivion. The oldest known black holes have existed for almost as long as our universe has been around, 13.8 billion years old, older even than the first stars. These ancient behemoths reside at the centers of galaxies, their immense gravity affecting not only nearby stars, but also entire galactic structures. They grow larger by consuming surrounding matter and merging with other black holes. In some cases, black hole collisions produce gravitational waves that ripple through spacetime itself, offering astronomers a unique way to study these cosmic giants. These events are so powerful they can cause ripples in the fabric of spacetime, detectable from billions of light years away. In the vicinity of a black hole, clouds of gas and dust swirl in complex patterns, drawn toward the event horizon by overwhelming gravitational forces. These accretion disks can extend for millions of kilometers, but are compressed to densities far exceeding those on Earth. As matter spirals inward, it heats up dramatically due to friction between particles, reaching temperatures that could melt iron instantly. This searing hot region is the last visible stop for any material destined to cross the event horizon. The process by which this gas and dust is drawn informs a dynamic structure known as an accretion disk, where matter orbits the black hole at incredible speeds. Black holes can evaporate over time due to Hawking radiation, but for a 5 solar mass black hole, this process would take approximately 10 million billion years. This phenomenon highlights how fleeting our current understanding is compared to the vast timescales involved in cosmic events. The energy emitted through Hawking radiation gradually saps the black hole's mass until it eventually disappears completely, leaving behind only a faint echo of its former existence. Each particle pair that emerges near the event horizon contributes to this slow evaporation process, marking the gradual dissolution of these cosmic giants over incomprehensible durations. The paradox of extreme density within seemingly empty space defines black holes, where a mass equivalent to 1.4 suns is compressed into an event horizon radius of just 4 kilometers. This boundary marks the point beyond which not even light can escape, illustrating how something immensely dense can exist in such a confined area. As you approach this boundary, temperatures at the edge hover around -230 degrees Celsius, colder than deep space, while the inner regions experience temperatures reaching up to 1 billion degrees Celsius due to extreme compression and friction. This stark contrast between coldness and heat within the same object highlights the complexity of black holes. Astronomers study these phenomena through indirect methods, since no light escapes once past the event horizon. They observe gas spiraling toward the black hole, heated by friction to millions of degrees Celsius, before disappearing into oblivion. This accretion disk reveals how matter behaves under conditions far removed from those on Earth, with temperatures and pressures that defy human experience. Black holes form when massive stars collapse at the end of their lives, compressing their mass into an infinitesimally small point known as a singularity. The oldest black holes are estimated to be around 13.8 billion years old, born in the early universe and influencing cosmic evolution ever since. These ancient celestial bodies have played a crucial role in shaping galaxies and regulating star formation. The process of Hawking radiation provides another layer to this paradox. Near the event horizon, quantum fluctuations create virtual particle pairs that momentarily appear and vanish. One particle falls into the black hole while its counterpart escapes, leading to an outward glow known as Hawking radiation. For a 5 solar mass black hole, this evaporation takes approximately 10 sextillion years, highlighting the vast timescales involved in these cosmic phenomena. Despite their immense gravitational pull, black holes do not uniformly distribute their mass within the event horizon. Most of the mass is concentrated near the center, with only a tiny fraction spread out across the boundary. This uneven distribution creates regions of extreme density and pressure, which are responsible for the unique physical processes occurring in these cosmic anomalies. The event horizon itself acts as a boundary where time behaves peculiarly, slowing down infinitely close to its edge due to extreme gravitational forces. For an external observer watching someone fall into a black hole, it would appear as if that person were frozen in time, never quite crossing the threshold. This phenomenon defies our intuitive understanding of how objects should move and interact under such conditions. Inside this boundary, space-time is so severely warped that any attempt to map its geometry using traditional coordinates becomes impossible. The concept of direction loses meaning within a few kilometers of the singularity, where tidal forces stretch objects into thin filaments, a process known as spaghettification. These forces are so powerful that they can disrupt atomic structures and rearrange particles in ways not seen anywhere else in the universe. Yet, despite this extreme environment, black holes maintain a delicate balance between their immense gravitational pull and quantum effects near the event horizon. The temperature at the very center of these cosmic giants reaches unprecedented levels due to compression and friction, yet the boundary itself remains surprisingly cool by comparison. This juxtaposition of heat and cold within such a confined space underscores the paradoxical nature of black holes. The first image captured of a black hole's shadow in 2019 revealed an unmistakable dark circle against a bright background, confirming theoretical predictions about their appearance. This visual evidence not only validates decades of scientific theory, but also provides a glimpse into one of the most extreme environments known to exist. The shadow itself is caused by light bending around the event horizon, creating a silhouette that marks the point of no return. Black holes represent both the ultimate endpoint for massive stars and potential gateways to other parts of the universe or even different dimensions. While their inner workings remain shrouded in mystery, they offer invaluable insights into fundamental aspects of physics, challenging our understanding of gravity, quantum mechanics, and the very fabric of space-time. As you draw closer to a black hole's event horizon, time dilates more profoundly for distant observers, while remaining normal for someone falling towards it. This creates a paradoxical situation where two observers experience vastly different timelines despite being separated by mere moments of subjective experience. Just outside the event horizon, temperatures plummet dramatically as matter falls into the accretion disk. Here, gases cool rapidly from billions of degrees to much lower levels, contributing to the complex dynamics observed near these cosmic giants. Understanding these temperature fluctuations helps astronomers infer how energy is generated and radiated away from black holes. Astronomers have discovered that gas falling into a black hole emits X-rays with specific energy levels, providing valuable clues about its properties. These emissions serve as fingerprints for different types of black holes and help researchers map out the accretion disk structure. By analyzing these X-ray signatures, scientists can infer details about the mass, spin, and environment surrounding supermassive black holes. In extreme proximity to a black hole, tidal forces stretch objects into long, thin shapes, a process known as spaghettification. This occurs within 10-20 kilometers of the event horizon, where gravitational gradients become so intense that they tear apart matter. Despite this destructive force, studying these regions offers insights into fundamental physical laws under extreme conditions. The first image of a black hole's shadow was captured in April 2019 by the Event Horizon Telescope. This remarkable achievement revealed a dark circle against a bright background, confirming theoretical predictions about how light behaves around such massive objects. Observing this phenomenon directly allows scientists to test general relativity and explore new frontiers in astrophysics. A black hole with a mass of 5 solar masses has an escape velocity at its event horizon that reaches the speed of light, 299,792 kilometers per second. This extreme gravitational pull warps time so severely that it appears to slow down or stop for distant observers near the event horizon. The closer objects get to this boundary, the more pronounced this effect becomes, leading to a fascinating distortion in how we perceive time and motion around black holes. The age of the oldest known black holes is estimated to be around 13.8 billion years, close to the age of the universe itself. These ancient cosmic entities have been influencing galaxies since their formation, shaping the structure of space through their immense gravitational pull. Their presence has played a crucial role in the evolution of stars and galaxies over billions of years. Black holes can evaporate over time due to Hawking radiation, but for a 5 solar mass black hole, this process would take approximately 10 sextillion years, far beyond our comprehension. This slow evaporation contrasts sharply with the rapid formation and growth of black holes in the early universe, highlighting the vast timescales involved in cosmic processes. Gas clouds orbiting a supermassive black hole at its center move in intricate patterns dictated by gravitational forces. These orbits are not uniform, but rather follow complex paths determined by the mass distribution around them. The closer these gas clouds get to the event horizon, the more their motion appears distorted and slowed down from an external perspective. The temperature at the center of a supermassive black hole can reach up to 1 billion degrees Celsius due to extreme compression and friction. This intense heat is generated as matter spirals inward, colliding with other particles in a process that defies our everyday experience of thermal dynamics. Despite this extreme environment, the laws of physics still apply, offering insights into how energy transforms under such conditions. The transformation from stellar mass black holes to supermassive ones is a process that unfolds over billions of years, shaped by cosmic events and gravitational interactions. A typical stellar mass black hole forms when a star with at least 13.8 times the mass of our Sun collapses under its own gravity. Once formed, it begins to accumulate matter from nearby stars or gas clouds, growing in size. As these black holes grow, they can merge with others through complex gravitational interactions. When two such objects collide, their event horizons coalesce into a single entity, creating a supermassive black hole. This process is akin to the fusion of celestial bodies, where the combined mass exceeds that of millions of suns. The resulting object has an event horizon radius that can span light years. At the center of these supermassive black holes, temperatures reach up to 1 billion degrees Celsius due to extreme compression and friction. This heat is generated as matter falls toward the singularity, creating a region where particles collide with incredible force. The energy released in this process far exceeds anything we can experience on Earth, yet it operates under the same fundamental laws of physics that govern our everyday lives. Over time, these supermassive black holes influence their host galaxies by regulating star formation and shaping galactic structures. They anchor entire systems, guiding the orbits of stars and gas clouds with their immense gravitational pull. This dynamic interplay between black holes and galaxies is a key factor in understanding how cosmic landscapes evolve over billions of years. Interestingly, some supermassive black holes are thought to have formed early in the universe's history, just hundreds of millions of years after the Big Bang. These ancient behemoths grew rapidly by merging with other black holes or accreting matter at a rate equivalent to several solar masses per year. Their presence challenges our understanding of how such massive objects could form so quickly in a young and relatively sparse universe. The eventual fate of these supermassive black holes is tied to their environment and the rate at which they accumulate mass. Some may continue to grow, while others might lose mass through processes like Hawking radiation or interactions with surrounding matter. This long-term evolution highlights the dynamic nature of cosmic structures and underscores the enduring influence of black holes on the universe's architecture. As supermassive black holes grow, they can reach masses billions of times greater than that of our Sun. These giants exert a gravitational influence so powerful that even light takes measurable time to escape their vicinity. The event horizon of such an object might stretch for hundreds or thousands of kilometers, depending on its mass. This vast boundary marks the point beyond which not even photons can break free from the black hole's grip. The process by which these supermassive black holes form is still a subject of intense study. Some theories suggest that they could have originated from the collapse of massive stars or through the accretion of smaller black holes and surrounding matter. In some cases, entire galaxies may merge, bringing their central black holes together in a cosmic dance that results in even more massive entities. This merging process is not instantaneous. It can take millions of years as the two objects spiral closer under the influence of gravity. Once merged, these supermassive black holes continue to shape their surroundings through powerful jets and outflows of energy. These phenomena are driven by the accretion of matter onto the black hole's event horizon, creating intense magnetic fields and relativistic particles that shoot outward at near-light speeds. These energetic emissions can influence star formation in nearby regions and even affect the distribution of gas within entire galaxies. The life cycle of a supermassive black hole is intertwined with the history of its host galaxy. As stars form and evolve around it, they contribute to the growth of the black hole through collisions or close encounters that send matter spiraling inward. This intricate relationship between galactic evolution and black hole formation highlights the interconnectedness of cosmic phenomena on vast scales. In some distant future, as galaxies continue to interact and merge, supermassive black holes will play an increasingly central role in shaping the universe's structure. Their influence extends far beyond their immediate vicinity, affecting the distribution of matter across entire galactic clusters. This long-term perspective underscores the profound impact that these cosmic giants. Time stops at the edge of a black hole, not for you, but for everyone watching from afar. Imagine standing just outside the event horizon of a black hole with 4 times our sun's mass. The gravitational pull here would stretch your body into thin filaments, a process known as spaghettification, occurring within 10-20 kilometers of the event horizon. This extreme stretching is due to the immense difference in gravity between your feet and head, causing internal organs to separate at a microscopic level. As you approach closer, the temperature near the black hole's center can reach up to 1 billion degrees Celsius because of intense compression and friction. The heat would vaporize any material that ventures too close, turning even iron into plasma. Astronomers have observed that gas falling into a black hole emits X-rays with specific energy levels, which are used to study its properties. These emissions provide crucial information about the mass and spin of a black hole, as well as the rate at which it consumes surrounding matter. The cosmic microwave background radiation provides clues about the universe's early state, including the presence of ancient black holes that formed shortly after the Big Bang. These primordial black holes could have played a role in seeding galaxies and influencing the distribution of dark matter throughout the cosmos. The connection between black holes and the cosmic microwave background reveals unexpected insights into the universe's origins. The cosmic microwave background is the oldest light we can observe, dating back to 380,000 years after the Big Bang, when the universe became transparent. This radiation permeates all space, offering a snapshot of the early universe's conditions. It also contains subtle anisotropies that suggest the presence of massive objects, like black holes, which could have influenced the formation of large-scale structures in the cosmos. Black holes can evaporate over time due to Hawking radiation, but for a 5-solar mass black hole, this process would take approximately 1067 years. This phenomenon occurs when virtual particle pairs spontaneously appear near the event horizon. One falls into the black hole while the other escapes, contributing to an outward glow that gradually saps the black hole's energy. The temperature of Hawking radiation is inversely proportional to the black hole's mass, meaning smaller black holes emit more radiation and evaporate faster than larger ones. This process underscores the delicate balance between gravity and quantum effects at play near a black hole. The age of the oldest known black holes is estimated to be around 13.8 billion years, close to the age of the universe itself. These ancient black holes formed from the collapse of massive stars in the early universe, when conditions were ripe for stellar birth. Their presence has influenced galaxy formation and evolution over billions of years. As you drift closer to this cosmic behemoth, time dilation becomes more pronounced, with distant observers seeing your movements slow down dramatically. For you, however, time proceeds normally until you cross the event horizon, where not even light can escape the gravitational pull. You stand just outside the event horizon of a black hole, time frozen for all who observe from afar, yet you feel every moment stretch and hum with possibility. As our journey through the cosmos comes to its quiet end tonight, I want to thank you for joining us on this peaceful voyage across the stars. Feel free to subscribe and leave a like if you enjoyed the trip. Good night, and may your dreams be as vast as the universe itself.